Hey, thanks for having me here. You'll see another perspective here. I have 10 slides to go through. I'll try to go pretty fast. I'm going to tell you a little bit about Paragon, a little bit about myself, talk about some of those challenges from the life support perspective primarily, and also talk about some design attributes and some important things that we need to cover. And I'll try to tie in everything we're covering here in these charts. I tell you about Paragon because we've talked about the economic part of the equation here. We're a for-profit company. Our goal is to build the hardware that these providers use, whether it's NASA or the commercial customers. And it's an important part of having an economy that thrives and has a reason to exist. We do a lot of cool things at Paragon. We're going to talk about the space things here. I'll just go across there, though. For Boeing, we're building a humidity control subsystem for a commercial crew. For Sierra Nevada, we're building the radiators for their Dream Chaser program. For NASA, we're building the brine processor. That's that part of the water system they've been talking about that gets you up to that 98, 99%, I think, water recovery. And then for for more NASA programs on Orion, we build some boring but needed tubing and plumbing and things like that. So a little bit about me, and again, this is for the students here too, so you can see how your career starts to maybe how you can build a career. This is just the way I did it. I started out at the University of Florida. I got 2 degrees there. I want to thank Purdue for winning that game this weekend as well. But what that did is it got me involved with some folks back then with the University of Florida that were working with Kennedy Space Center, the Controlled Ecological Life Support Program. And that got me exposed to scientists and plant physiologists and horticulturalists. And boy, if you're an engineer, you want to work with a bunch of scientists because they always need things and they can't build them themselves. But that got me involved from the life support side, doing bioregenerative life support. And again, as an engineer, immediately what I saw was technical challenges that had to be solved. And of course, the scientists are doing much more important things, growing smaller sizes of wheat, growing plants that use less water, use less light. But everything starts to come together, so it's those different disciplines working together. I went on to Johnson Space Center. I worked for Honeywell and Hamilton Sundstrand. I was fortunate to be able to work on site at NASA, working directly with the government on a lot of projects, able to publish papers and present and get involved in the community. And again, I encourage folks to do that. Then I did a stint at Bigelow Aerospace. We talked about them. We did life support there. So we, for those first 2 vehicles, we put 2 vehicles up. I don't know if people realize that. They're still in orbit. The life support part of it worked. It was an inflation system, and they're still inflated as last I've heard. And just one thing I want to say that Bill mentioned, he mentioned the word balloon. I'm actually a big proponent of inflatables. I encourage you, if you guys are looking at the architecture and how you implement them, they're not really balloons. People think of balloons and they pop and they fail catastrophically. They actually fail very gracefully, and you can seal a leak with a duct tape, literally. And then Paragon, I'm the chief engineer here. We do, again, a lot of cool things. We do things in near space, and we'll talk about some more things. So habitats. You're going to see this is kind of a background for myself and Paragon. There's my time at Bigelow. We were starting out, this was before they got into some of the, this came after I was there, but we were doing some of the early packaging of the ECLIS down that central core, how to use that efficiently for ducting and plumbing and utilities. Inspiration Mars. This is when we worked. This was about 4 or 5 years ago now. This is a commercial-led effort to take 2 people and circumnavigate Mars. Tremendous excitement. A lot of good initial technical work was done on that, and you'll see a common theme here in a minute where the funding just doesn't come through. Lunar Gateway, we've supported 2 teams there. I'm not showing any pictures on that because I can never figure out what you're allowed to show. But a lot of good work going on there. That's NASA's effort to focus near-term habitat. And what I would just say on that is a focus. People were talking about what do we need when the requirement's good enough. You need a mission is what you need. You got to have a mission. You got to drive to a date. You got to work to meet your commitments by the dates that are established. And that's what Lunar Gateway does. Mars 1, very controversial, right? I thoroughly enjoyed the work that I did for Mars 1. It was great to not get paid by NASA, or a government agency, to do work on Mars programs. We did 2 studies there. One was the initial conceptual look at EVA and establishing the requirements, the basic requirements, what I call driving requirements for a mission like that. We also looked at the habitat ECLIS, and went hard back and forth with those folks that you weren't going to grow plants right out of the gate. You're going to have stepping stones. So when you look at all these start to be some of my, what I'll call gaps or the challenges. There's similar technology problems, and I think Larry talked about this, reliability. It's huge for the equipment we're trying to build. If you do the numbers, someone loves their car they've got 200,000 miles on it. If you figure they drive an average of 40 miles an hour, that's like a grand total of less than 200 days of operation. And just think about a car that's highly developed, countless iterations and designs, how much maintenance, repair, refurbishment goes into maintaining a car that will drive 200,000 miles. So to build these systems, it really is about reliability. It's building unprecedented levels of reliability. And that's a real challenge for engineers, especially when you add any level of complexity, pressure, temperature, or chemistry going on within that unit process. Another one, for all of these economic reasons, like for Bigelow, to get away from real-time Earth-based control and support. But as you move further away from Earth, we know that's a reality. The moon's 3.5 minutes, Mars is 20 minutes or more. And those are real challenges, because right now the way all space programs operate is basically Earth-centric control, command and control. And then finally, people have been talking about this, economic reasons, but sustained funding. You can look at all of these approaches, and none of them have gone forward and flown. I can think of countless government-led programs that haven't gone forward and flown and developed. They're not doing the mission. And so that's one, we're not going to solve it here, but I do encourage you, the one way we can contribute to this is that first bullet up there where I had affordable. We have to look at realistic, affordable solutions. And I was talking to Julio there, I think, even for the academics, when you're developing these new technologies and new approaches to doing things, try to look at the practical and how it can be applied, not at the end of your career, but at the beginning. So here's some challenges, and these are, entry, descent, and landing. How it impacts us here is that mass that we got to put down. There's limitations to how much these vehicles someone else is going to build that can take our hardware there. Tightly controlled landing ellipse, not only getting it down, but then getting it close. If you don't get it close, your habitat or your structure has to be moved into position. Radiation shielding, we've talked about that, lava tubes, piling up regolith. Earth-based supply and logistics, this is important. The lower cost of transport people have been talking about. It's going to be critical. If we're going to go anywhere, if you think of any mission of exploration, there is trade back and forth. There's materials coming. In early days, it's coming one way. And that has to be there, so you got to think about that being there. On the surface, it's diurnal and seasonal temperature extremes, navigation, surface navigation of rovers doing the EVA, visibility extremes, Mars dust storms, waste management and resource recovery. That's one of the areas I've worked in mainly. I don't even have a main slide on this one. Electrical power, this is my first red one. So I'm an ECLIS guy, and someone else's propulsion, and someone else's guidance, navigation, control. Nothing, if you think about this habitat, until we're far, far in the future and it's totally bioregenerative based and it's using direct solar illumination, nothing is more important than electrical power, because if you don't have that, then your mission, you cannot persist on the surface. So here I have a few habitat-specific challenges. I think I'm doing okay on time. So food supply, it's going to be resupply initially. You know what? It works. We're doing it. Biomass production eventually. So what are the challenges, though? The challenges right now, in the short term for resupply, it's shipping logistics. It's getting, again, the stowage space and volume, and mass and volume on those spacecraft coming to Mars. And shelf life, I put a question mark there. I know the food folks at NASA JSC maybe say we're not quite there, but I see some of those preppers. They got some food that lasts a pretty long time. So I don't know if that's a big a challenge, but I'm also presenting these in general order of what I consider criticality. Biomass production, one of the challenges when you're doing this to make enough food to keep people alive, it's the energy, it's the automation or the lack thereof, if you think of modern agriculture. There's mass and volume allocations that go along with it. It's huge steps up in volume you need to make enough food to keep a person alive. And it's new. It's new to NASA and it's new to the space community. Really? Wow. Okay. Okay, so let me go fast. Water recycling. We can talk more about these at the breakout session. Water, you got to recycle it. Physiochemical initially, hybrid bioregenerative eventually. Again, it's the same basic problems, mass, and again, the electromechanical complexity of physiochemical. And then stepping up to bioregenerative and food, the water recycling through the plants. You can get basic condensate is pretty clean. And one of the funny things with mass is we always want to make it better, so we get that water so clean. We get it so clean we have to add minerals back to it, otherwise you'll do bad things to your body. So atmospheric composition, physiochemical, the problems there, and then bioregenerative again, I think this is the way it'll go. It's the same thing here though. Now here's the big one, atmospheric pressure. It's you guys building the habitats and the structures. There's persistent challenges from now until the future, until we go out. And there's one is containment. We have to contain that atmosphere. Again, people die in seconds without an atmosphere. So the way to do that is you've got to find ways to build these habitats where we can expand them continually. I think you're always building new pressurized volumes. You're finding new ways to storage it. And then it's all the access. And those are definitely not my areas, but that's one of the biggest ones. ISRU, I'm out of time, I know. But ISRU is huge too, and I put this as red because we haven't done it. When you consider everything that goes into it, lack of pressure, temperature extremes, energy, all of those things, we just haven't done. Robotics and automation, just a huge problem. And then I think this is critical for long-term in situ manufacturing. Again, it's essential for long-term, and when you think of manufacturing today and all that's involved in it, energy and things like that, and lack of automation, it's just hard to see that as not one of the greatest problems. And finally, just for the engineers out there, I know I'm out of time, dissimilar redundancy is incredibly important, regenerative technologies, habitat structures, all these things. We think of different ways to do the same job. You talk about camping. It's better to have more than one way to get something done. Don't put all your eggs in one basket. Maintenance repair at the lowest practical level, common interfaces, common components. We've got a lot of work to do. All right.
Question from the panel.
No one?
Time.
Nope.
So do you see the possible combination of inflatable as well as maybe hard printed structures? Do you think that's something that might have a potential benefit?
Yeah. So that I was going to ask you about that. What are your factors of safety, and where's the pressure seal on your printed structures? And again, I would say that's a great application because then you can have the structure do its structural work, and you have a low cost or lightweight thin membrane that's doing the pressure containment.